Okay, let's go to forced oscillations. We're going to add another term. Make this really, really complicated. Okay. Folks, follow the important stuff. Don't get bogged down in the mathematics. I throw a lot of higher level math in here just for the benefit for people who are taking those higher level math courses and they want to see an application. Okay, so we started out with Newton's second law, which we always start out with when we want to predict the motion of an object. The simple harmonic oscillator only had this one term, negative kx, all right? Then we added this drag term to it to basically say, well, there's going to be internal friction and frictional forces that are going to slow this oscillating object down. Now, to really throw things for a loop, I'm going to add this extra equation right here, or extra part of the equation. And what this is this is an outside force which is oscillating, not necessarily at the frequency that the harmonic oscillator likes to oscillate, but it's producing this time-varying oscillating force on the system. And I want to find out how the system is going to behave. Okay, so I'm not going to even bother to go over the differential equation here. Here's what all the terms look like. Okay, so it's actually a pretty nasty equation. It can be solved, but not going through that. Its solution looks something like this. Okay, now it looks very much like simple harmonic motion. Got this cosine omega t, but we have this new function which is frequency dependent, and what this is going to do is essentially give us an amplitude, and omega 0, represents the frequency of what the harmonic oscillator likes to oscillate. Omega represents the frequency of the oscillating force that we're going to put on it. Okay, let's get away from the math. It's really a much higher level course than this. If we graph amplitude as a function of the frequency, and you can even write this with omega instead of this f here. Okay, there are no units here, so we can write it this way too. What we see is that this driving oscillating force is going to have the biggest effect, not surprisingly, when we use it to drive the harmonic oscillator at its natural oscillating frequency. Again, omega is equal to the square root of k over m. That's where it really likes to oscillate. Okay? Now, for some systems, there's not much damping. Here, what we get is a very sharp peak where at a very particular frequency, that object's going to oscillate very hard, but not so much at other frequencies. The strange thing about the damping, however, is as we increase the damping, it really affects the amplitude a lot at resonance, but not so much at other frequencies. Heavy damping, you get almost no peak at this resonant frequency. Now, this is actually, it actually has an electronic analogy too. This is actually how the first radios were actually created, where they had this resonance or resonant frequency in a very particular type of circuit called an RLC circuit. Okay. All right. So again, here again is plotting the amplitude as a function of damping. The damping does change the resonant frequency a little bit. What it does is it decreases the resonant frequency because, as you might expect, you're slowing this down a little bit. But again, here is the driving frequency. This is the omega, which is driving this thing to oscillate. All right, you're like, okay, what applications do we have for this? Well, many systems have these resonant type reactions, okay? You can actually demonstrate this. If you hit a tuning fork and it's next to a resonance box, the sound waves from the resonance box can travel to another resonance box and actually start another tuning fork to oscillate. Now, you might see this a lot of times or hear this a lot of times when you have different machinery and they cause other things to vibrate in the room. Maybe you're down doing your laundry someplace and the dryer's on spin. And as it spins faster and faster, it starts vibrating at a particular frequency. And other things in the room, which have a similar resonance frequency, also start oscillating with that. Okay? And skip this right here. I guess another example would be, which would be similar, would be a person pushing a swing. It's not quite a sinusoidal, force which acts on the swing. It's more like a push, 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 but you're always pushing, pretty close to the resonant frequency that this pendulum, person on the swing, likes to move back and forth, okay? If you push at the wrong time, you're not going to increase the amplitude of the swing. You can actually pull on the chains on the swing too to get yourself oscillating back and forth if you do it just at the right time. The other example is a wine glass. You've seen the example where a soprano starts singing and wine glass shatters and you're like, oh, well, how'd that happen? Well, once again, you've got a system which has a resonant frequency, okay? It has a frequency at which it likes to vibrate, okay? Glasses like to vibrate at a very particular frequency, but they're also very brittle. They'll break very easily if they bend back and forth. Now, I'm not aware that there's any singer with a strong enough voice to do this, but we typically take the voice at a high pitch, a pitch that matches the resonant frequency of the glass. We amplify it so the frequency of the sound waves are equal to the resonant frequency of the glass, and the glass starts shaking back and forth, okay? Actually, there's this resonance modes where it'll squeeze back and forth, back and forth, back and forth. And eventually, if the amplitude becomes too large, we'll see the breaking strength of the glass and boom, it shatters. So again, it's good to understand this type of effect more in terms of conceptual, because as you saw, the equations are really, quite difficult to understand. But again, just about any system has different resonant modes, okay? Has different frequencies at which it likes to vibrate. If your car isn't perfectly aligned, you might have a little bit of a shudder, and you might hear that resonance cause other things to oscillate. As I said, a laundry dryer will do that. But when engineering things, we have to be aware of these resonant frequencies. And in 1940, engineers became very aware of something that they had not considered. Now, the Tacoma Narrows Bridge is a suspension bridge. And because the cable, why isn't this drawing? Because the cable, so it swings down like this, and then it has different cables right here, we don't have to worry about, pendulum-like frequencies all being the same. It's really suspended from different lanes. So for the most part, back and forth swinging isn't really a problem for the bridge. What the engineers didn't consider is because they made the side panels of the bridge solid instead of allowing the air to flow through them. As the air tried to flow past it, it would create vortexes, which would happen at a regular period. Okay? These vortices would have low pressure and they pull on the bridge as they went past, and then the bridge would swing back, and then another vortex would be created. The problem here is the frequency at which the vortices were created were equal to the resonant frequency of the bridge in this torsional mode. Okay? Objects can have different modes which they can vibrate back and forth, side to side. In this case, this is a torsional mode. And once the wind got too strong, the amplitude became so large that eventually it exceeded the breaking strength of the cables. And as you can see, bad things happen when the bridge comes down. Now, fortunately, this behavior had been going on for a few days. All right. So nobody wanted to be on this bridge in the first part. In fact, there were some cars that were still left on the bridge when people became very nervous and abandoned their cars. But eventually, as people watched this, the bridge began to fatigue, and then it collapsed. Unfortunately, the outcome wasn't the same in 1989 when the Loma Prieta earthquake struck San Francisco and Oakland. Here, this overpass right here also had a particular resonant frequency. Now, this resonant frequency, unfortunately, was matched with the frequency of the earthquake. And as the earthquake shook the roadway back and forth, the columns were under more and more stress. And eventually, even though they were reinforced concrete, the frequency of the earthquake being very closely matched to the natural frequency of these elevated freeways led to disaster. And people were lost as the top level collapsed on the bottom level. So again, this is actually something that engineers have to take into account, right? In physics 1, we talked about Newton's first law. You need to make sure that all the forces cancel out to make sure the structure, can hold up. Well, here we can see there are other, processes that work, like these dynamic processes, where if you have some periodic force acting on an object, it can be periodic in terms of turbulence from airflow. It can be periodic in terms of shaking from seismic waves. You have to engineer against these types of resonances.